Recording. Okay, now we're back. I just wanted to point out, so again, we'll start out. GHGL is a component that's available through the package manager. If you're using Rhino 7, I would install the latest version, 7.0.3. If you're using Rhino 6, I believe 0.6.4 was the last version that really worked in Rhino 6, and there's still quite a few bugs in that version. So I would, if at all possible, just use the Rhino 7 version of this. All right. I think what I'll try to do is get a basic shader going, and then start tweaking it and show you guys some of the basic capabilities. There's so much involved here. And it's, it can get pretty deep pretty quick, that I kind of want to just try to inform people about just the basics of what you can do. So I'm going to make a curve. Well, I've already made a curve, and then I'm going to draw it in a bunch of custom different ways. So let's see, start with the slider, divide a curve, make some points, and make a GL shader. I'm going to feed those points into the GL shader. The default pre-canned GL shader is just one I wrote that currently takes vertices and a color or colors as input. So I'm just going to get color going here. Feed that in. And then if I turn off preview for these guys, because they're right on top of each other, yeah, we can see that I'm actually feeding in information. This GL shader is doing the actual drawing in Rhino now, because the preview is off for these other guys. So what's happening here is I've got this set up as a scripting style component where you can define different inputs that you want, and then those inputs would be interpreted by the shaders as either an array of inputs. And the shader would be interpreting each item in that array as a different pass through the shader, or as a single value that could be globally set across all the shaders. And so if I go to edit code, well, actually, I think I'll back up here. If I go to my, if you right click on the shader itself, there's a few different ways that OpenGL can draw the inputs. Right now it's set up as points. So every single point that's being passed in is being drawn as an individual entity. We could also draw them as lines, where every 2 points that get passed in, are drawn as lines, or line loops and line strips, where it's the line strip in this case makes the most sense, where the point and then its previous point get put together, and you make a continuous line out of that. So if we look at this in different ways, you have lines would be every 2 vertices would be interpreted as an individual line. Loop just kind of ends the very last point and the first point. They'll come together. And strip is all these lines are joined together. And so you can kind of probably zoom in. There's not enough point. There's too many points here probably. But if I lower the resolution, you can see that this is not really a curve. This is just drawing line segments themselves. I also have options on the shader to change the line width to, say, 15 or something like that. There's hard-coded limits in OpenGL for what those line widths could be. They usually stop around 16. And so when you're drawing lines, it would draw them as nice thick lines. And if I change my draw mode back to points, there's a point size, say 20 or something, but normally around 16 or something is about a limit of what you would have for OpenGL. So what's happening here is every single point that's being passed in, and I'm going to go to the shader itself now. Every single point that's being passed in is being run through this program, which is called the vertex shader. And the vertex shader takes every single point and manipulates it in a way that ends up being in in a 1-by-1 clipping cube, you might want to say, and that information gets passed down. Once it passes depth testing and whatnot, it gets passed down to a fragment shader. Fragment shader, in this case, since our points are very large, there's actually, the fragment shader is being called for every pixel that OpenGL thinks that that point is supposed to be covering. And these are just little programs. So in this case, I've got vertex set as input, and I've got vColor set as input, and I'm using a built-in global variable, you might want to call it, which is a uniform, to convert this vertex from its 3D points position to a 4D point position. That's basically what you need to do inside of a vertex shader. If I go to the uniforms, there's actually quite a few built-in ones that I've got here already set up. So let's say we wanted to actually do something here. If I wanted to just take my colors, and I have the code editor is set up now, so it actually compiles live on the fly, and I keep updating. So if I wanted to change my vertex color, dot R, so it's RGBA equals 1. You can see that it's actually updating the color. And I could control that externally from Grasshopper. So let's say I wanted to come back here, and I zoom in, and I add a variable, and I call it red, let's say, because I'm just being that creative. I hook up a slider to it, and I come back into the code, and there's a single input going for red. So now I have to actually say, all right, I know that I need a uniform as a single variable that's applied to all of the vertex shaders at this point, and it's of type float, and I'm going to call it red. So I need to match this with the name of a variable, and then here I'm going to change this to red and zoom back out, and didn't work. Oh, wait, no, it did. It's just because there's so much green involved there. You can see it changing. What else can be done here? So since we're actually manipulating the, we're actually trying to draw custom stuff here on the screen. We can do whatever we want with all of these points. And we can say, all right, well, we know that we're passing it a vertex. We could say, let's see what these vertices look like here, actually, in XY. Okay, so we got some on the plus side of the X and some on the minus side of the X. So I could use this vertex input, and I could say vertex color B equals 1, but only if vertex.x is greater than 0. Right. So I just ramped up the blue value when you're on one side of the x-axis. So that's interesting. Okay. Well, let's take the curve. We'll re-parameterize it so we get a value from 0 to 1, and I'm going to feed these t values in here. So t, pass that in, go into the shader, and this syntax looks a little weird. It could actually just be in float curve T, but GHGL needs to be tuned up a little bit to be able to detect that. Okay, and so now I could say vertex color dot B equals curve T. We'll just get rid of this stuff. Probably have to hit F5 to restart it. And you can see that as it's traveling from 0 to 1, the color is actually changing based on the curves T. And again, it probably might even look better if you actually did it as a line strip. So you have a nice gradiently changing curve based on its parameter value. Okay, so let's see where I'm at here. A little scattered after the Zoom bombing thing. So, what I was going to try to get to was having a really interesting looking curve with a bunch of different, or really interesting looking point or curve with a bunch of different changes made inside the shader itself. So I'm going to go back, change it to points, and I can see that I'm drawing individual points here. And I set up an equation for changing my color right here. I'm just going to look up what I did here before. So I'm going to have some value, and it's going to be, I'm going to use the sine function. So there's a lot of different built-in functions in GLSL. So sine, cosine, absolute value. An easy way to look that stuff up is just GLSL, and then, so in this case, mod or sine. Usually takes me to it right away, all these reference pages. And those are all supported right inside of GHGL itself, because we're really just on the fly compiling shaders and then sending them down to the graphics card. Let's do sine of some big number, and we'll multiply it by curve T, so we get something that's changing. And we want the color to be in the range from 0 to 1. Sine goes from -1 to 1, so we'll do +1, and then divide it by 2, right, times 0.5. And you can see that while I was typing, it was blank. If I have a typo also, it should actually show up down here and tell me that I made a mistake on the fly. I basically am looking at keystrokes, and if you haven't typed for more than a second or something like that, I try to recompile on the fly and redraw. So let's see, this color, we'll make that C. And so now we're getting some kind of a repeating effect, right? Because there's sine and there's a large number. And actually, instead of using this number, I think I'm going to change this. So let's get rid of this slider, make a new one. Rename this guy to repeat. Go back to the code and change red to repeat. Change this value to repeat. I think I deleted red earlier, so everything should be fine. Sometimes I have to hit F5 when I actually make changes. And so now you can see that the repeat is basically because the sine function is there. What other cool stuff can you do with this? Since there's built-in uniforms for all these different things that could be happening. Let's see. There is one for time, and there's time delta, but time is every time the frame is drawn, you get an updated number. So you can do animations basically while this is running. So I'm going to go to my uniforms section here, and I'm going to insert time. And then let's see, I'll adjust my equation here. So I have plus underscore time. All the built-in ones that I've made, I prefix with an underscore so that autocomplete works and you can kind of tell which are the built-in items. Let's see. Is that actually making a difference? Oh, it is. Yeah. It's a little bit hectic. So I'll just take time and I'll multiply it by some number to get to slow down. There we go. Okay, so the vertex shader is being called over and over and over. Well, sorry, Rhino's repainting over and over and over again. And every time it repaints, the vertex shader itself is getting called. And as time gets updated, it's just adjusting colors on the fly. Let's see, and what did I end up with here? So what I'm doing here in the vertex shader is I'm figuring out a color and I'm figuring out a position. I don't really need to figure out the color here. The color is something I'm actually passing down to the fragment shader. This is the output. So by default, a vertex shader always passes out a position. But you can define as many outputs as you want from the vertex shader that get passed down to a fragment shader. And so I think I'll make another output here. I'm going to make one out vec3. So these different data types, vec3, vec4, vec2, and float are usually what you would work with. Those are the, that's a single float, 2 floats, 3 floats, 4 floats, and then a map4, I believe, is the 4x4 matrix. Those are typically the common data types that you would use. Vec4 is used for color also, so RGBA. In this case, I just want to take a vertex and I want to pass this vertex down to the fragment shader. So I'm going to name it something like FS vertex, just to mean that I'm going to pass this down to a fragment shader. And I've declared it as an output. So I'm just going to say FS vertex equals vertex. And then if I go to my fragment shader, I don't have any input set yet for the fragment shader and for the vertex, so I'm going to just define a new one. I'll say in vec3, give it the exact same name, FS vertex. And now this vertex value is being passed down from the vertex shader to the fragment shader, and that means that every single pixel that the fragment shader is running at, it's getting the vertex. So what can we do with that actually? Well, here the fragment shader is actually figuring out what the color is that should be drawn. And so we could say if fragment color dot R is greater than 0.5, then we're just going to throw away those pixels. Right. So now we get pixels being thrown away based on their color. Or what I'm going to try to do here is I'm going to turn off time because it's a little annoying. Just make that 0. So it's always the same spot. What I'm going to try to do here is I'm going to, since we're drawing these points, I'm going to get rid of the center, so they're nice circles, and maybe even put a little dot in the middle. Let's see. Turn my count down so you can see the individual points a little better. And to do that, now that I've passed the actual vertex down, the 3D vertex down, I can figure out where the center of that specific vertex is in relationship to where this pixel is being drawn. In order to do that, I added a few functions to GHGL that are kind of easy to use helper functions. And to get to those, you go to Edit, Insert Function. And so I've got clip to screen and screen to clip, closest line. This basically finds a t value along the line. I can talk about that later. And then a world to screen. So convert 3D world coordinate to a 2D screen coordinate. So I'm going to insert that. And what this does, this line here, is it actually adds a function that you can call later on. This is a nice clean way to look at the code, but also a nice way to do it is I just have this function here called GLSLFI code, which takes this function and basically unpacks it into the actual full function. So we can see what's going on. Let's see, so that basically just brought this entire function in, world to screen, brings in, inputs a 3D point, asks if you want to have the upper left as the origin, upper left corner as the origin, or the lower left corner as the origin. A transformation for world to screen coordinates, and the current viewport size. Now the world to screen and the viewport size are actually built-in uniforms that I've got. So if I go to uniforms, let's see, I was looking for world to screen, add that, and uniform for vertex size. So now I can actually figure out that I want to get a screen coordinate. So I'm going to vec2 screen equals world to screen. The fragment shader vertex that I'm being passed in. Upper left or lower left. I want lower left because I'm going to use this to compare against a built-in OpenGL variable that tells you where your pixel fragment is. Let's see, world to screen transformation. So that's this guy. And viewport size. So now I have a screen coordinate. And OpenGL has, at the fragment shader level, it has something that's called the GL frag coord, which tells you exactly where on the screen that pixel is that's being drawn. So what I can do is I can add a little function here that says, I'm going to get a distance. I'm going to use the distance function in OpenGL, which is going to get the distance between two 2D points, 2D locations. So I'll get the screen point that I just figured out, and there's this built-in GL frag coord, and I just want its XY values. And now I can say if that distance is less than some number, say 3, we can discard, and you can see I'm like actually getting little holes taken out of the center of the pixel. And we could hook this up to a slider too. So might as well do it. So here, add one called gap. And we'll make that 0 to 20. Up, go to the editor in the fragment shader. I'm just passing in a single value, so I'll give it as a uniform float gap, semicolon, and no semicolon, that was L. And for the distance now, I'm going to say if the distance is less than gap, I'm going to throw that pixel away. So if we come over here now, you can see that I can actually start making holes. You know, and you can do other cool stuff too, right? So if it's less than the gap, but it's if the distance is greater than let's say it was less than gap and distance is greater than 2, then we'll discard. So that'll actually leave a little dot in the middle, right? Yeah. And we could, you know, we can change the color too. Say if the distance is less than or equal to 2, then my fragment color is black. Right, so we get nice little black centers there. And let's see. Let me turn time back on now that we've made it a little less annoying. Change the draw mode to line strip. And for line strip, I think this thing's already, the line width is 50. Draw mode's line strip, 15. Oh, there we go. So if I make the line nice and wide, it's got the same effect, right? And then, you know, you could do other things along here too. We could, as you're moving along T, you could say, well, you know, we can make little dashes on the center and stuff like that too, if we want to just discard pixels as we move along. But pretty cool. So any questions so far?
One question, if I can jump in, Steve.
Yeah.
How does this? How's the performance if you scale this up? Is it compared to like native if you're working with dots and points inside Grasshopper? Because this is just affecting, from what I understand, the pixels on the screen.
Yeah. Yeah. So this is going to be a lot faster. When you change the inputs, a solve has to occur inside of Grasshopper, and so that's just going to be standard Grasshopper speed for actually solving. But once I get, say, you know, 1,000, I don't know, let's change these values, you know, say 10,000. Once I get these values, I actually just upload all those values to the card, and if they don't change, I don't do anything. So I just keep calling the GPU with that same set of data over and over again. So it's actually quite fast.
All right.
Yeah. So there you go. I mean, it's still moving along. My computer is set at a 60 frames per second VSync here, so that's basically as fast as it can get right now. Right? Does that make sense?
Yeah. And I have to add that I think it looks amazing. There's so much like possibilities popping up in the brain when watching this.
There's a lot that can be done here, and I'm trying to keep it relatively simple at this point, because I completely glossed over another tab here called the geometry shader. I have nothing here, but basically a vertex shader can pass data down to a geometry shader, and then a geometry shader can actually add more vertices. And that's how we actually do things like sprites and stuff, and we can start making the lines have variable width, or you know, having variable size points, maybe arrayed across the surface or something like that. So it's deep, it's geeky, you know, but it works really well. And this is actually what I've been using to get the display to work in Rhino itself. It's a great prototyping tool. The other nice part about it is since it's all self-contained, you can just share it with other people, and that component will just work.
Do you expose some global stuff like the background the background bitmap or the environment map, just in case we want to do something like refraction, for example? Can we get access to those global information?
We don't. I don't. We can definitely add as much as you want.
Yeah.
You know, it's basically right when Rhino's done drawing its main geometry, it calls this, and so we could add background color or anything like that. I don't know if you've seen these tooltip previews showing up on the screen.
Yeah.
Those are the depth and the color buffers that can be passed down to further on to other shader components as texture inputs. So you can start doing really fancy like post-processing effects and stuff. That makes sense.
So it's actually possible to have a shader that apply on the entire 2D screen with the depth information and like the global noble information for post-processing, right? So if you want to do like my own version of screen space ambient occlusion, it should be possible, right? I should have all of the noble and the depth information there. Okay.
Yeah, and I would recommend. I mean, probably what I would recommend is get the open source GitHub repository, which is GHGL. And in there, I have a directory called samples, which has a few samples. Yeah. Really, the spot to look is deep inside sources tests. This is just I haven't really documented them well enough. But if we go in and we start opening, let's see. So GitHub, GHGL. Well, if I go to samples first, I think I've got post effects in there already. Yeah, so we could do, let's do pixelate, let's say. Oops, I'm hitting test max speed. I make a sphere.
If I want to do like post-processing the entire screen, then I will have to generate a fake geometry that like cover the entire viewport, right?
Right. So here I'm actually here I am doing that actually. This one is, I'm probably just making a decision. The fragment shader. T is the horizontal position. Yeah, I'm splitting it somehow. Not seeing it offhand, but I can actually show another one that's probably a better effect. Well, this is a fun one. So here we're actually passing in, this is just passing in -1, -1, and a quad, basically, that's getting mapped to the entire screen. And then inside of the shader itself, I'm getting the color buffer, which is everything that's drawn up to the point where the shader has kicked in, and then I'm using that as a texture and then applying effects on top of it. Right.
Yeah. And if you have multiple situations like that, then they will use the sorting order to know which one will come last, right?
Right. Yeah. I try to figure out the correct sort order for when these shaders are chained together, but yeah, it's really hard to do it just right. So there is a sort order in there. And so let's see. I can actually show in the source and the tests. There's some nice simple tests are actually in here, and there's some that get kind of complicated, but probably people like Toon Effects. Let's see, what did I just do there? Open. Oh. Oh, it's much smaller, that's why. So, if you wanted to see how like toon shading is done and stuff like that, all these are in the test. And if you look at the shaders, they're actually quite small. In this case, this is one of the mesh shaders. It takes a mesh as input, and there's some built-in attributes to say, do you want the mesh vertex? Do you want the mesh normal? What are the others here? texture coordinate or the vertex color. In this case, I need the normal. I take that normal, I pass it down to the fragment shader. And in the fragment shader, there's a built-in uniform that says, you know, what are the lights in the world of camera transformation. And I basically take the normal of the mesh vertex, and I convert that to camera coordinates because I know that this light is actually in camera coordinates. And I figure out how bright a pixel should be based on the normal and the camera direction. And then in this case, I mean, I think I could just say, I can comment these two out. And this is basically standard shading. And then all I'm doing here is I'm kind of banding the shading by multiplying, converting to an int, and then dividing back out. So I kind of converted these numbers into hard bands, let's say. Right. What else?
Okay. Just want to confirm that the entire rendering pipeline in Rhino is based on forward rendering, right? There's no deferred rendering here.
That's correct. That's correct. For this, that's true. There's deferred I mean, well, so deferred rendering, you mean draw to a bitmap and then use that bitmap for other stuff, right?
Yeah, like do all the bitmap and do the lighting as the final step rather than compute the lighting in the fragment shader, but yeah.
Right. So some of our stuff is deferred rendering, and some of our stuff is just regular forward rendering. Depends on the display mode you're in. Yeah.
Yeah.
Yeah. So, I think that's mostly what I wanted to show today. Hopefully that's a good start. And no Zoom bombing today, so that's good. Any other questions? Do you want me to try to do this again with maybe some more advanced features with the geometry shader or something?
Yeah, that'd be great.
Okay.
That would be cool. Yeah.
Yeah, I think
mean,
geometry.
Like those topics are more specific to the GS shape, the GS shader language itself. But
yeah,
you can do a demo right.
Yeah, because I think. So let's see. Here's a sprite sample. I think something like this would actually be useful, because this is using geometry shaders to draw these circles. Because I've got a single point that I'm passing in, but then I'm expanding those points out into quads, and then I'm texturing those quads also. I use basically if you have a string that gets passed in to the shader, and that file is in the same directory as the Grasshopper definition, then I can pick up on what that image is that you want to use. So, cool. Okay. Thanks, guys. Hope you're having a good day, and let me know if you have more questions, and we'll take it from there. Cool.
Yeah. Thanks a lot. That was very
Thanks, Sid. Thank you.
Thanks, Steve.